In section 5.2, we're going to start examining what happens when two objects collide. We're going to start studying collisions. We're going to start off simple. We're going to start studying collisions in one dimension or in a straight line. And collisions are governed by the law of conservation of momentum. The law of conservation of momentum states, when two objects collide in an isolated system, the collision does not change the total momentum of the two objects. Whatever momentum is lost by one object in the collision is gained by the other. The total momentum of the system is conserved. So we can state that m1 v1 plus m2 v1 is equal to m1 v2 plus m2 v2. It's best to understand this by trying a sample problem. Let's try sample problem number 1. A hockey player of mass 97 kilograms skating with a velocity of 9.2 meters per second south collides head-on with a defense player of mass 105 kilograms traveling with a velocity of 6.5 meters per second north. An instant after the impact, the two skate together in the same direction. Let's find the final velocity of the two hockey players. Note that the final velocity for hockey player number 1 and for hockey player number 2 will be the same. So we know that the initial momentum is equal to the final momentum. This is the law of conservation of momentum. So we know that m1 v1 plus m2 vi2 is equal to m1 v final plus m2 v final. And I haven't denoted the final velocities with separate subscripts for object 1 and object 2 because the two final velocities will be the same. In fact, we're going to use this to simplify our calculation. So we have m1 vi1 plus m2 vi2 is equal to final velocity times m1 plus m2. Notice how tedious it is to make sure you're denoting the initial and final momentum components as the first object, the second object, and the initial and the final. Please be careful. That is often a source of error when doing these calculations. Solving for final velocity, we rearrange. We get m1 vi1 plus m2 vi2 divided by m1 plus m2. We can sub and solve. m1 is 97 kilograms. v1 is 9.2 meters per second south plus m2 is 105 kilograms. Now, the second velocity is 6.5 meters per second north. So what I'm going to do right off the bat is change the sign and the direction so that it matches the first. So we can compute this algebraically. So we get negative 6.5 meters per second south. All of this divided by 97 kilograms plus 105 kilograms. If we punch this into our calculator, we end up with a final velocity of 1.0 meters per second south. All right, let's take a look at sample problem number 2. Here's a problem that deals with an asteroid. And we're going to try to make sure that this asteroid avoids the Earth. So as it's approaching the Earth, we're going to split it in two and make sure that they travel in opposite directions with enough distance so that they clear the Earth. Let's read this problem. In a science fiction novel, a large asteroid is approaching the Earth. Scientists decide to use an explosive device to blow the asteroid into two equal halves before impact with the Earth. The asteroid has a mass of 2.4 times 10 to the power of 9 kilograms. For each half to safely miss the Earth, an explosion must cause them to travel a minimum of 8.0 times 10 to the power of 6 meters at right angles away from the Earth within 24 hours. Assume this is a one-dimensional problem. The magnitude of the impulse applied to each fragment is the same, but the halves are directed in opposite directions. So let's see what we know. We know that the initial momentum is equal to the final momentum. It's the law of conservation of momentum. We know that we want each of these halves to travel 8.0 times 10 to the power of 6 meters in 24 hours. So we can use this to calculate or determine the final speed of each of the halves of the asteroid. So speed is equal to distance over time. We want to report this into meters per second. So 8 times 10 to the power of 6 meters divided by 24 hours. Let's convert the hours into seconds. And we do this by multiplying by 1 over 3600. If we do so, we end up with a speed of 93 meters per second for each half of this asteroid. Remember, one asteroid will be traveling north and one asteroid will be traveling south. So let's find the final momentum for asteroid half number 1, which is the mass of half number 1 times the final velocity of mass number 1. So we know the mass is 1.2 times 10 to the power of 9 kilograms times a velocity of 93 meters per second. And let's include a direction. If this is asteroid half number 1, it will be traveling north. So punching this into our calculator, we end up with a momentum of 1.1 times 10 to the power of 11 kilograms times meters per second north. We can do the same for asteroid half number 2. We can find the final momentum for asteroid half number 2. Mass number 2, final velocity number 2. They are equal halves, so they have the same mass, 1.2 times 10 to the power of 9 kilograms. This time with a speed, again, of 93 meters per second, but directed south. Punches into our calculator, and we end up with the same magnitude for the final momentum, but in an opposite direction, this time south. If you add up the final momentum, you find the total final momentum, 1.1 times 10 to the power of 11 kilogram meter per second north, plus 1.1 times 10 to the power of 11 kilogram meters per second south. You can guess, or confirm, rather, that the total momentum, if you added these up, would be 0. Initially, this asteroid is at rest, and then when we split it in half, it's traveling in two opposite directions. So the before equals the after, and the law of conservation of momentum is conserved. In part B, they want us to determine the impulse delivered to each part by the explosion. Impulse is force times time, and it's equal to the change in momentum So we know that impulse is equal to mv2 minus mv1 . In this case, we know v2, and we know that v1 was 0 because the asteroid, before it was split in half, was at rest. So if we do this, we end up with a mass of 1.2 times 10 to the power of 6 kilograms times a speed of 93 meters per second. And for the first asteroid, this is in the direction north, so the impulse is 1.1 times 10 to the power of 11 Newton seconds. Remember that Newton second is equivalent to kilogram times meters per second. When talking about impulse, F delta T, I'd like to always report it in Newton per second. So the explosion will deliver an impulse of magnitude 1.1 times 10 to the power of 11 Newton seconds to each of the fragments. Please review these concepts by doing practice problems on page 231 and review problems on page 232.